All right, if you're on Zoom, please type something into the chat to let me know that you're here. The roll sheet is getting passed around for everybody who is physically present. Today's lecture is largely a review of the different types of amplifiers that we saw in Engineering 221. So if you have any questions about the homework or anything like that, I'd be happy to answer them before we jump in, because I don't think this lecture is going to take the full hour and 15 minutes. Anybody got anything they want to address before we jump into op amps? All right. So the first op amp circuit that I would like to look at then is what's called the unity gain buffer. All right. In a unity gain buffer amplifier, we apply our input signal Vin to our non-inverting input terminal, and we have a negative feedback loop from our inverting input terminal to our output that contains no resistance. It's literally just a wire that connects our inverting input to our output, and we measure our output voltage signal at the output pin of the op amp. All of the examples that I'm going to work today are negative feedback amplifiers, so we're going to be using the ideal op amp rules in order to analyze them and develop their relationships. Also, we are going to assume that all of the amplifiers have sufficient values for VCC plus and VCC minus that they would operate. Okay, so all of these are on and working within the linear range is the assumption that we're going to make here. So if we apply ideal op amp rule number 1, which says that the current flowing into this terminal is 0 and the current flowing into this terminal is 0, and we apply op amp rule number 2, which says that the voltage present here at our non-inverting input node must be exactly equal to the voltage present, the voltage present at our inverting input node must be equal to the voltage present at our non-inverting input node. We see that that wire has a potential of Vin, and so we get Vout is exactly equal to Vin, and we can have a closed loop voltage gain defined as Vout divided by Vin is exactly equal to 1. So some of you may be asking a pretty reasonable question. Why on earth would we build an op amp that has a gain of exactly 1? Why wouldn't we just connect our input signal directly to our load? A unity gain buffer is used in instances where we need to exploit the fact that our op amp has an infinitely large input impedance. So if we had a very sensitive sensor, so say it was like a pressure transducer or something like that. A pressure transducer is a device which converts a change in relative pressure, usually because due to a fluctuation in the position of a diaphragm, into a small output voltage. Typically speaking, they cannot generate a lot of power. They generate reasonably large voltage signals, but can generate extremely small currents. So we would need to use a unity gain buffer like this in order to have that voltage signal be capable of actually driving some output load or anything like that. If we connected a resistor or something like that directly, we wouldn't actually be able to see the input signal. So the unity gain buffer provides isolation between the input source and the output load. Has a gain of exactly 1, and so Vout exactly follows Vin. If we were looking at this guy under the practical op amp rules, we would see that actually the gain is the open loop voltage gain divided by 1 plus the open loop voltage gain. So for very, very large values of open loop gain, it's going to look really close to 1. But if we had a poorly designed amplifier, it wouldn't actually settle to 1. It would just be some fraction of the input. So if you're going to use the unity gain buffer, you need to make sure that the open loop gain is considerably large. All right, so let's look at another one now then, unless anybody has any questions on this guy. So now let's look at a non-inverting amplifier, and it's going to be pretty similar to a unity gain buffer with some key differences. So as before, we apply our input voltage to our non-inverting pin. We're going to measure our output at the op-amp's output pin. And we are going to have a feedback path between the output pin and the inverting input terminal. And we're going to put a resistor in this feedback loop. I'm going to call this resistor R2. One other thing that we are going to do is we are going to replace a resistor. I'm going to call it R1 between the inverting input terminal and ground. So if I didn't have that resistor R1, this would literally be the exact same thing as a unity gain buffer. Because no current could be flowing through that resistor R2, so the output would be exactly equal to the input. So if we apply our ideal op-amp rules, where we have 0 amps flowing in here, 0 amps flowing in here, and I have some voltage V minus at the inverting input terminal that is going to be exactly equal to the voltage present at our non-inverting input terminal, meaning that is Vin. I can use voltage division, and I can say that Vin is exactly equal to Vout multiplied by R1 over R1 plus R2. So what I am suggesting is that I have some fixed output voltage that is dropped over resistor R2 and resistor R1, and the output voltage sees those two resistances in series because I know that none of the current flowing through those resistors can branch off and flow into my input terminal. Using voltage division, where I have a known voltage drop over these two guys, I can find the voltage at the node in the middle, and I can rearrange this, and I will find that our output voltage is then 1 plus R2 over R1 times Vn, which means I have a closed loop voltage gain, AVCL, of 1 plus R2 over R1. This is probably a little bit different than the way I derived it in the video you guys may have watched in Circuits 1, depending on when you took it. But to me, it's probably the easiest way to figure out what's going on here. Any questions? Typically speaking, we would follow the currents and all kinds of jibber jabber like that, which is absolutely something we can do. But this voltage division approach gets us there real quick, so that's why I chose to do it today. Anybody got anything? All right, so I see some nods of assent. So let's move along to our next example, which will be the inverting amplifier. All right, so the inverting amplifier. I want to point something out here. I am flipping my op amp over, so I'm placing my non-inverting input terminal on the bottom now, my inverting input terminal up at the top. I'm going to ground my non-inverting terminal. I'm going to take my output at the op amp output pin. Go away thing. I'm still going to have my negative feedback resistor labeled as R2. And I'm going to place a resistor R1 between the inverting input terminal and my input voltage Vn. So fundamentally, just to be real clear here, the difference between my non-inverting amplifier and my inverting amplifier is that I have transposed where I put ground and where I put Vn. So if I can get this table out of the way without causing it to collapse. If we look at this guy, Vn is on the non-inverting input terminal. Ground is placed on this leg of R1 that isn't connected to the inverting input terminal. If I swap those, I get this guy. That's the only between the two. It's just changing where I place ground and where I place Vn. Applying my ideal op amp rules. I know that this guy is 0 amps. This guy is 0 amps. This voltage right here, V minus has to be what? 0, right? So if my input voltage, let's just argue for right now that it's positive, but it really doesn't matter. But if my input voltage is positive, I should observe some current I flowing through resistor R1, and that current has to continue on and flow through resistor R2 as well, because it can't branch off and flow into the input terminals. So I can say that Vn over R1 has to be equal to 0 minus V out, or negative V out divided by R2. And I can rearrange this guy and see that V out is simply negative R2 over R1 times Vn, which means I have a closed loop voltage gain, AVCL, of negative R2 over R1. Just to be super clear here, for the inverting amplifier, my input signal is applied through a resistor to the inverting input terminal. For the non-inverting amplifier, my input signal is applied to the non-inverting input. So it's another way we can tell these guys apart since they are so incredibly similar. So these are the basics. They provide basic levels of amplification. A couple of notes real quick here. For the non-inverting amplifier, the smallest voltage gain that we could ever get would be 1. If R2 were much smaller than R1, this settles to a gain of 1. So this guy can only be used to boost the level of a signal, right? So the output is always going to be larger than the input. Our inverting amplifier can both boost our signal strength and attenuate or make smaller our signal strength. The drawback to having that increased functionality is it is always going to provide us an inverted signal, meaning if our input is positive, our output is negative. If our input is negative, our output is positive. We always see a phase shift of 180 degrees when using an inverting amplifier. Any questions on these three basic guys? All right, let's move along to the weighted inverting summer. Yeah, I got enough in here. Summer, S-U-M-M-E-R. So this is one of our first op amps that's performing a mathematical operation. It is extraordinarily similar to a non-inverting amp, excuse me, an inverting amplifier. As much as my non-inverting terminal is grounded, my output is taken at the op amp's output. I'm going to have a feedback resistor, and I'm going to call this guy RF. You'll see why momentarily. Placed between my inverting input terminal and my output terminal. And now, between my inverting input terminal and my input signals, I'm going to replace resistances. So I'm going to say that I have some resistance R1 placed between VN1 and my input terminal. I have a resistance R2 placed between my input 2 and the inverting input terminal. And I have a resistance R3 placed between my input 3 and my inverting input terminal. And I could continue this scheme on for really an infinite number of input signals, assuming that my output wouldn't be cut off or saturated by saturation distortion. So that's really the limit. I can add almost an infinite number of small signals together and be okay. But if I try to add large signals together, I'll probably exceed the output range of the amplifier. So, as per usual, we will apply our constraints. No current can flow in here or here. And the voltage drop at this node, V minus, has to be exactly equal to 0 volts because our non-inverting input is connected to ground. So if we apply Kirchhoff's current law at the inverting input terminal, I can see that I have a current I1, I2, and I3 flowing in, and a current of IF flowing out. And so I can say that I1 plus I2 plus I3 is equal to IF, which gives me VN1 over R1 plus VN2 over R2 plus VN3 over R3 is equal to negative V out divided by RF. And from this, I can see that V out is negative RF times Vn1 over R1 plus Vn2 over R2 plus Vn3 over R3, etc. I can't really describe a closed loop voltage gain for this system because there are multiple inputs, but I could describe it for each input and it would simply be negative RF divided by the resistor attached to that input. So this is a weighted inverting summer because it sums or adds together all of our input signals, but each one is applied a specific weight based on the ratio of RF divided by Rn. So if we want input signal 1 to be boosted more, we make R1 smaller. If we want input signal 1 to be boosted less, we make R1 larger, and so forth. We can make an inverting summer by setting R1, R2, and R3 all equal to the same value, right? So if R1 is equal to R2 is equal to R3, then V out is simply negative RF over, I'm going to call it R1 just for argument's sake, Vn1 plus Vn2 plus Vn3. So this is an inverting summer because all of these signals are added and they're all scaled by the exact same amount. So that's why it's not weighted. So this guy is a little bit more tricky than our last example. I'm trying to decide if I want to look at a non-inverting summer. We can look at one, but they don't really have a whole heck of a lot of use. So if I look at it here, I won't need to look at it elsewhere. I'm only going to do 2 inputs because the math's going to get real ugly real fast. So that's the biggest reason why we don't use it. So a non-inverting summer is going to look something like this. All right. So the analysis of this guy can be a little difficult. All right. In my opinion, the easiest way to analyze this guy would be to use the superposition principle, where we look at it with one input signal on at a time and then add the results together at the end. Okay. So if we did such a thing, let's look at it with just V1 on, or VN1 on. Our circuit would look like this. What to do? Scroll up there we go. So here's RN, here's RF, here's R1, here's VN1, and here is R2. Right? So this is with VN1 on and VN2 off or shorted to ground. So we apply my constraints. So here's where things get arguably a little difficult. What value is my non-inverting input terminal voltage going to have? Absolutely correct. Yeah. So effectively, each of our input signals is going to see a voltage divider at the input. So in this case, we are going to have a voltage of VN1 multiplied by R2 over R1 plus R2. The voltage present at this terminal just sees a non-inverting amplifier, right? If we know what the voltage is here, and we just treat it as if we had applied an input voltage of this to everything to the right of this node, we have just a simple inverting amplifier, or excuse me, non-inverting amplifier. So we can see that V out prime in this case is going to be VN1 multiplied by R2 over R1 plus R2 multiplied by a factor of 1 plus RF over Rn. What changes when we ground VN1 and apply a signal to VN2? Yeah, so that is exactly right. The only change we would see is in this voltage divider equation, where instead of having R2 in the numerator, we would now have R1 in the numerator. So we can see that V out total is going to be VN1 times R2 over R1 plus R2 plus VN2 times R1 over R1 plus R2. This whole thing gets amplified by a factor of 1 plus RF over Rn. You can see pretty easily now why having more than 2 inputs makes the math on this guy just go berserk, right? So a non-inverting summer does have its uses, but a inverting summer has significantly more uses. And as you'll learn on Wednesday, you could simply cascade it into another inverting amplifier to get your output signal to be positive. And then it's a little bit easier to use. All right. Let's jump ahead now to, that was too many pages. A differencing amplifier. So this is going to be our first configuration wherein we're applying a signal to both the inverting and non-inverting inputs. So let's call this guy R4. This guy R3. This guy will be VN2. This guy R2. And this guy R1. And this will be VN1. So we have an input signal applied to our non-inverting input, and we have an input signal applied through a resistive network to our inverting input. This is another instance where using superposition makes our life much, much easier, right? So with VN1 on and VN2 off, Vout prime is going to look like what? Anybody have any thoughts? So VN2 is grounded. So if VN2 were grounded, how is that circuit any different than this exact circuit? It isn't, right? Just the labeling of our resistors has changed slightly, right? So we have a voltage divider applied to our input signal, and then that signal is going to be boosted by a gain of 1 plus the feedback resistance over that input resistance. So we can see that Vout should be, let's see, VN1 times R2 over R1 plus R2, this whole thing multiplied by a factor of 1 plus R4 over R3. With VN2 on and VN1 off, what do we have? So VN1 is off, right? So we have this resistor R1 placed between this node and ground, and this resistor R2 placed between this node and ground. So R1 and R2 are in parallel, so they just look like some equivalent resistance, right? But they're connected directly to the non-inverting input terminal. How much current can flow through them? 0. So the voltage drop applied at this node has to be 0. So with VN1 off, this is just a simple inverting amplifier. There's just a resistor placed between the non-inverting input terminal and ground that doesn't really do anything, doesn't have any effect on our output signal. So we should see negative VN2 multiplied by our feedback resistor of R4 divided by that input resistance of R3. When we put all of this together, Vout is equal to VN1 R2 over R1 plus R2 times 1 plus R4 over R3 minus VN2 R4 over R3. So it takes the difference of our input signals, but it scales input signal 1 by some factor and scales input signal 2 by some other factor. If R1 is equal to R2 is equal to R3 is equal to R4, meaning we use the same size resistors for everything, what is our input-output relationship? Somebody tell me what's going on here. So let's look at this guy right here. So if R1 is equal to R2, then I have R2 over twice R2. So really this voltage is just being multiplied by a factor of 1/2, right? Then I have 1 plus R4 over R4. So I multiply Vn by 1/2 and then multiply it by 2. I just get Vn. Or Vn1, excuse me. This guy over here, R4 and R3 are identical, which means this guy is also scaled by a factor of +1. So I simply have Vn1 minus Vn2. So it literally just takes the difference of those two signals when all of our resistances are equal. That is a much more common application than changing the resistor values and scaling one side and scaling the other by some different amount. This is really how you would mostly, practically, this is how you would see this when used. This should look similar to mean test questions I asked in circuits 1, to put it bluntly. All right, so we have amplified signals, we have attenuated signals, we have added signals together, we have subtracted signals from each other. The last two operations that I can do with an op amp that do not involve using a transistor in the feedback loop, which you guys aren't ready to see yet, would be integration and differentiation. So I can do calculus with op amps as well. You guys haven't had Math 245 yet. Okay, so I have to do it the hard way. All right, it's not that bad. I just have to remember, okay, I'll tell you what this one is after I draw it because I don't remember which one is which. So, I'm going to ground my non-inverting input terminal. I'm going to take my output there at the output of the op amp. And I keep saying that because there are certain op amp circuits to where you don't actually take the output of the system at the output terminal of the op amp. So we're not going to see any of those in this class, but it does happen. I'm going to place a capacitor here in the feedback position and a resistor here. And this is going to be V out as a function of time. And this is going to be V in as a function of time. Okay. So if I apply my op amp rules, I have no current flowing into either of the input terminals. I have a voltage, V minus, that is 0 volts. And from that, I can then observe that I'm going to have some current, IR of T, flowing through my resistor. And that same current flows through my capacitor. Because I have a time varying current flowing through my capacitor, I will observe some voltage change over my capacitor. And we need to recall that the current flowing through a capacitor, IC of T, is equal to C times the derivative or we need to look at it the other way. VC of T is 1 over C times the integral from 0 to T, or actually I'm going to say negative infinity to T of IC tau d tau. No, IC x dx, okay. I'm doing this integration specifically from negative infinity to not have to include a DC offset or some initial condition on my capacitor voltage because we know that the change can't be abruptly. So I'm saying that if I integrate from T is equal to negative infinity where the capacitor was not charged, I'm good to go here. Mathematically, all that's doing is making the math a little bit simpler and making us not have to put a resistor in the feedback loop in parallel with that capacitor C, which makes the relationship more hard to observe. So that's a analog electronics thing when we start making the math harder. All right, so IR of T is going to be equal to Vn divided by R, which means Vc of T equal to 1 over C integral from negative infinity to T of Vn divided by R is 1 over RC to T of, sorry, I missed a dt there. Vn of x dx, where x is just a dummy variable for time. So how can I relate Vc of T to V out? So what's the nodal voltage at the positive polarity terminal of Vc of T? 0. What's the nodal voltage at the negative polarity terminal of Vc of T? V out. So V out is exactly equal to negative Vc, right? Because voltage, but with opposite polarities. So this leads me to V out is equal to negative 1 over RC integral from negative infinity to T of Vn of x dx. So obviously this guy is an integrator because our output signal is a scaled version of the integral of our input signal. So let's write that down up here. The integrator right here is a fundamental building block of control systems, analog control systems, more specifically. You will get beat to death by this circuit over and over and over again, and its variations if you choose to theory when you're a senior. It's very paramount to how most modern control systems work. Our differentiator differentiator. So yes and no. So that's a fantastic question. So let me answer that. Okay. In this circuit right here, if I replaced C with an inductor, or if I replace that capacitance with an inductor, I would absolutely get a differentiator. That being said, you very, very rarely see that happen. And the reason you rarely see that happen is because the tolerance level on an inductor is very, very large. Whereas the tolerance, meaning the tolerance on the component value of a capacitor, is much smaller. So to have a more stable and more well-defined integrator and differentiator, we always use capacitors for everything. Now, as it turns out, I'm a jerk, and on your homework assignment for this stuff, I literally ask you to derive the relationship if there is an inductor there. It's extraordinarily similar to the capacitor relationship and all that kind of stuff, so it isn't particularly difficult. But in practice, it would be extraordinarily rare for you to actually make one of these integrators or differentiators with an inductor. You would 99.9% of the time use a capacitor for it because it gets a more stable signal that's more well-defined. So what we are going to do for the differentiator is simply flip where our resistor and capacitor are placed. And that gives us the opposite mathematical relationship. That was a very good question, though. So now we will place our resistor here. Here's V out as a function of time. Dang it, now I'm drawing an inductor. Got inductors on the mind now. That's all right. Here's Vn of t. It's my capacitor. So if I apply my ideal op-amp rules, this current is 0 amps, this current is 0 amps. The voltage at this node, V minus, is exactly equal to 0 volts. So we are going to have some capacitor voltage, Vc of t, which causes some current, Ic of t, and that current, Ic of t, then flows through this resistor, which is what winds up giving us our output voltage. So by inspection, hopefully, we can see that the N of t is equal to Vc of t, and therefore our current Ic of t is C dVn by dt, using our other current voltage relationship for a capacitor, right? The current flowing through a capacitor is the capacitance multiplied by the derivative of the voltage across the capacitor. That is the exact same current that is flowing through our resistor. And so we can say that V out, or actually, I guess a better way to put this would be, this is the same as negative V out divided by our resistor value. So I'm saying that the current that flows in, Ic of t, is equal to the current flowing through the resistor, which using Ohm's law is 0 minus V out divided by R. And then I can rearrange that guy, and I get V out as a function of time is negative RC dVn by dt. And so this circuit gives us a derivative-based relationship between our output signal and our input signal. So we have done addition, subtraction, scaling, attenuating, integration, and differentiation, all with an op-amp. That's why an op-amp is called an op-amp, because it does mathematical operations on analog signals. And the Army engineers that invented it shortly after the beginning of, I believe, World War II, couldn't think of a more clever name. All right, I think that's all the different types of amplifiers that we could really look at without just getting obtuse for the purposes of wasting time. So like we can make non-inverting differentiators and integrators, but all they wind up doing is just adding the input signal back in. It really doesn't change anything, and you really don't ever see them. So unless anybody has any questions on any of this noise, we have wrapped up for today. All right, so there's going to be a homework assignment posted within the next 20 minutes or so. It will be based on our lecture last Friday and today's lecture. So all in one thing. So you can work them. If you want to be really mean to yourself, the problems that say let me think of a better way to put this. The first couple of problems are using the practical op-amp model. Everything past that, if you don't use the ideal op-amp model, you're just making things really difficult for yourself. So keep that in mind. All right. There's the roll sheet. All right. Thank you, guys. See you on Wednesday.